we are now recording, and I think for the first time in several weeks, I don't, well, yes, I do. Okay. I didn't do this in my first class, I forgot about it. Oh, yeah, two things. Should have said one earlier, but better to put it on Screencast-O-Matic anyway. First, over the weekend was midterm, okay? We are now in the second half of the term, okay? We're a little behind probably where we ought to be, but I think we're making decent progress, okay? But that means, well, I forgot to mark you here. Let me do that before I forget it. Good deal. Thank you. Okay, March 6th, I hope it is, right? And Richard is here. All right, got it. Okay. Now let's get back to the announcement I was starting to make. The midterm was over the weekend. This is the first week of the second mini-term. Now, on the academic calendar, it says this week we are to submit midterm progress reports, which means that I submit to them if they open it up. They sometimes forget to open it up. But if they open it up, I'm required to submit all students who have D's or F's at midterms, which means I need scores, folks. And this class is especially deficient in that area. No papers have been turned in. In fact, let me look just quickly. The only class of my 7 classes that have not turned in a single paper, okay? Boo hiss, okay. Number 2, you had the first test for a while. And of all my classes, it's the, not quite. Nope, yep. Nope. Differential equation class. They turned in, 2 of them have turned in papers, but none of them have turned in the first test. So you're not quite alone there, but I need a score by the end of the week, okay? If they ask for us to do. Otherwise, I have to put that you're failing at midterm. Not that it's going to matter that much in the long run, but then you might get being bugged by come and see a counselor, come and see you. I don't know, but try to get a paper in, either the research paper or your first test, or both. Okay, that would be great. All right. Sorry I didn't say this last week, or maybe I did. I don't remember if I did or not. I tried to announce it to all the classes last week. So try to get those in. Now, that's one. The second effect of being in second mini-term is that my first mini-term physical science class is over, and tomorrow I start my second mini-term physical science class. The thing is, they meet at different times. The first one, and you don't really care about when they meet, but you don't care about maybe when my office hours are. For the first mini-term, they were on Tuesday, Thursday, 10:45 until 12:30. Second mini-term, starting tomorrow, 10:45 to 1:15. So I have longer office hours, which means I'm here later in the evening. I'm here till 5:45, both days, Mondays and Tuesdays and Thursdays. Which means for tomorrow, which is another announcement, I guess I should, I don't mind making this at all, is that tomorrow everyone in Jefferson County is voting for or against and voting about the school tax renewal. It's not a new tax. It's to continue the tax as always has been there, to keep it from terminating. Because I heard on the news this morning about a third of the county's budget comes from that tax. So if they don't have that in place, which has been in place for years, it's just renewing it. It just had a termination date. They have to renew it. So please, I would encourage you to go vote. I'm not going to tell you how to vote, but please vote. It's an opportunity. Never miss an opportunity to vote. So please vote. All right. Enough said. Off the political agenda. Any questions on anything we've covered so far? All right. We're in 3.4. And as far as I can tell from my note, we're just starting 3.4 today. can't find any marks on the page, so I assume we finished problem 3.3 last time. I'm glad you're here. I'm talking to myself. And, my first class started off with no students here, and after about half a page or so, one student came in, and then about a page and a half, another student came in. So I finally had two people to talk with. Hopefully we'll get a second one. All right, rates of change. Recall that the notation for the average rate of change we had back in pre-calculus 112. Average rate of change was change of y's over change of x, which looks pretty familiar, doesn't it? What does that look like? Okay, it looks like dy dx now that you know that, but thinking back in pre-calculus algebra, what would that have looked like? Or even earlier math. What is change of y over change of x? Slope. Yes, that would have been your slope. Exactly. Nicole is here. So half the class is here. I had half a class earlier this morning. I have half a class now. Maybe this is half class day or something. I don't know. So average rate of change back in pre-calculus algebra was alpha of x. Back then we called it alpha of x plus h minus alpha of x divided by x plus h minus x, which would have been just h. Now we're doing alpha of x1. Well, actually we did this too. Alpha of x1 minus alpha of x0 over x0 minus x1. Why is that true? Because alpha of x is y. Okay? So, same thing we had before. Slope formula and the delta y over delta x looks an awful lot like a dy over dx, and indeed that's what it is. Now, okay, but this is average rate of change. Average rate of change. If we change that to instantaneous rate of change, in other words, we're letting the delta x or the denominator get smaller and smaller and smaller, approaching 1, then this becomes a limit because that can't, it's approaching 0. It can't equal 0, so then we make this a limit, and then we have exactly dy dx, as you said, okay? Because that is what you get down to. So this is average rate of change. Here is instantaneous rate of change. It's taking that same ratio, okay? The limit of delta y over delta x as delta x is close to 0 would be the limit. The other way of expressing that is x1 is approaching x0 of alpha of x1 minus alpha of x0 over x1 minus x0. And that then would be why they don't put it in Leibniz notation dy dx, which is the same as f prime x0. That's the instantaneous rate of change. So here we're getting, rather than a theoretical limit, now we're talking about something from physics, okay? Rate of changes in physics or any other things. Usually we omit the term instantaneous and refer to the derivative simply as the rate of change. The shorter and also more accurate when applied to general rates because the term instantaneous would seem to refer only when it relates to time. And this could be related to anything else, miles per gallon, or something like that. Time is not involved, so what is instantaneous? Okay. All right. And it also says, keep in mind the geometric interpretations. The average rate of change is, of course, the slope of the wrong. Okay, go back. Hit the right key. Yeah. The average rate of change is your slope of the secant line. If this is your curve that represents the position, say, of a particle or whatever it is it's representing, then here it is at some initial position, here it is at some later position. Your delta y or delta x is the slope of that secant line between those 2 points. So the average rate of change is the slope of the secant line, whereas yeah, as you let that second point approach the first point, come down the curve, down the curve, down the curve, until that difference in x is 0, which is not allowed, but also your difference in y is 0 if it's a continuous function at that point. If it's discontinuous at that point, you have no way of getting a derivative or instantaneous rate of change. Because it, yeah, but that doesn't make sense physically. You don't have jumps like that, I don't think, ever. I want to say never, but generally you do not have those physically. So as this is approaching, the x1 is approaching x0, f of x1 is also approaching f of x0, if indeed it's a continuous function, which generally it is physically. Then the instantaneous rate of change, or the rate of change at x0, is a slope not of a secant line between 2 points, but of the tangent line at that point. Okay? So that sort of ties the practical with the theoretical, which we've been doing all along, I think. Now they mention the Leibniz notation, dy dx, is particularly convenient because it specifies that we are considering the rate of change of y with respect to the independent variable x, because y is a dependent variable. The rate of change dy dx is measured in units of y per x. That could be, if y was miles and x was gallons, that would be miles per gallon. Y was miles and x was time, that would be miles per hour, or feet per second, or meters per second, or whatever the things were. If it was cubic feet per minute, flow rate of air, whatever it is, whatever the units of y divided by the units of x. Again, this is heading much more toward physical, realistic examples. Okay? Okay. So here is example 1, given by this table of data. Now, these are data from the Mars Pathfinder mission in July 1997. Wow, it doesn't seem like that long ago, but it is. Okay. Now, all we have are these discrete measures. Okay? We got a measurement at 542, 611, 640, 709, 738, 807. 836, 905, 934. Okay? Those are not particularly evenly spaced. They're not badly spaced, but they're not. See, you're dropping 2 here and 2 there. You know, 2 here and there and there. Yeah, I guess they are very evenly spaced. Okay? But it's not a regular spacing that you would do. What is that? That's the 18 minutes and 19 minutes between each 2, isn't it?
Oh yeah, well I was talking about from 2, you know, it's
58 minutes between these 2.
Yeah.
So half of that would be 29 minutes. 29 minutes between each reading. So they are regularly spaced, but it's not just a normal number, 29 minutes.
Yeah.
Just happened to be that's what they set it up for. Okay. So we don't have a continuous representation of time, but neither do we have a continuous representation of temperature. But guess what? Time is continuous, and the temperature on Mars is continuous. You don't suddenly have a jump from 74 to 40. You can't, just like we can't here. It's going to happen slowly over time. I mean, it may advance rapidly, but if you had a chart recorder on it, you would see the spikes go, but always there would be a point in between every value. So these are continuous data. We just have selected points for those data. So then it kind of makes sense to talk about average rate of change. It makes it a little more difficult to talk about continuous rate of change. Instantaneous rate of change, because we don't have the minutes in between or even the seconds in between or anything else, okay? But we can still do it because we know this is a continuous thing. So it says calculate the average rate of change of temperature T from 6:11 in the morning, which is the second entry there, until, I lost my place, 9:05 at night, which is next to the last one that we have. So let's do the average rate of change between these two values. Of course, I've got to shrink back between these two values. So what is your average rate of change? Okay, that would be,
delta y over delta x
okay,
equals, f of x, or f of x1, so, let's see, that would be 6:11.
okay. You certainly can do it that way, okay, except that usually what's listed first, time is the independent variable, and temperature would be the dependent. So if I were doing this, I would write that as delta T over delta T, where capital T is temperature and little t is time. Okay? What does that give you?
Negative 71.6.
Okay. And again, it's okay to do it that way. Normally you do the T1 being the larger and T2 the smaller. I mean, the first, second, but it doesn't matter because it's going to be a ratio and the signs are going to cancel out. But okay, negative 44.3 minus
71.6.
Okay, I'll put that in parentheses so you don't have two minus signs next to each other.
So what is okay? 905 minus 611.
Okay, 611 is pretty tall. Okay, never mind. Okay, all right. That top number would be no, I did it backwards. Sorry. The eraser didn't work. Okay. Try that again. 7. 27.3, and that's positive over, now here you might have to do 905 minus 611, that would be a 4, and here we're going to borrow an hour, and that would be 60 minutes, so no, 6, okay, 6, 60, the 0 would go there, 54.
So 2 hours and 54 minutes.
Now, probably, what do they want this in? Minutes? I think they do want it in minutes. No, they want it in hours. Okay? So that would be 54 minutes. Let's see, 54 minutes times blank. Yuck, I don't know where my pen's going today. Okay. Is it? Okay. What I was trying to do, if I could blank hours. I'm trying to convert from minutes to hours. Here's how I do conversions. I put 2 blanks after it and try to match up first the units. I'm going from minutes to hour. One of these going on top, one on the bottom. Which goes where?
If you're trying to cancel them, wouldn't it go?
Yes.
Let's see. Would it go on bottom?
Which goes on bottom?
Minutes.
Minutes, absolutely. Minutes go on bottom here. Hours on top. And then you match the numbers to go with units. How many hours in a minute or minutes in an hour? 60 minutes in 1 hour. And what you were doing in your head, I think, was saying this was 19 over 20. Yeah. And 19 over 20 would be 0.95, right? Okay, so that's 0.95 hours. Okay, if I could get the pen thing to come back. And then we had the 2 in front, so it would be 2.95 hours. So this is degrees Celsius, I believe it was. Wasn't it?
Yes.
Yeah, degrees Celsius over hours right there. Okay? And so do the math. Get your calculator. 27.3 divided by 2.95. 2.95. 9.4. The book says 2 degrees Celsius per hour. 20.
That's a pretty long, even if you round it, it's 9.254.
Okay, 27.3. Oh, here's what they did. They didn't use 0.95, they used 0.9. I don't know why. Okay, I think yours is more correct. What is that? Did you use 9.5 or just 0.9? Okay. Huh? 9.5. You did. 27.3 divided by. Okay, you got. Oh, 254. Okay. I was looking at the book. They said 9.4. Okay. So. Yeah. Okay. Sorry. 9 point. Let's call it 3. Okay. 9.3 degree. Well, because for some reason they rounded the 54 minutes into 2.9. Did I do that wrong? I don't think so. Do 54 divided by 60. Okay, make sure that is 54, is it?
0.9.
Yeah. 0.9. Oh, it's 0.9? Not 0.95.
But that doesn't make sense.
On your calculator, it says 0.9. Or you got 1 decimal or 2?
It'll do as many decimals as need be. This just said, let's see, one more time. 54
divided by 60.
0.9.
Oh, yeah. That's. Okay.
Unless it's, let's see, 57 divided by 60. Yeah, no,
That's 8. It's not 19, it's 18 over.
Right.
18 over 20, which is 9 over 10. Okay, that's where it came from. They were right. Okay.
I said that.
Okay. 9.4 degrees per hour. Okay. That is correct. They got it right. Okay. It's 2.9, not 2.95 hours. Yeah. Okay. It wasn't the calculus giving us problems, it's the math. Okay. Now, the rate of change is the derivative, and they use the dt, where capital T is temperature, little t is time. Okay? Which is equal to the slope of the tangent line through the point. Oh, wait. It says use figure 3. Now, figure 3, they indicate they do have a strip chart recorder, which is connecting these points. And here they are looking for the instantaneous rate of change. Use figure 3 to estimate the rate of change, and they don't say instantaneous, but rate of change at t equal 1228. Oh, completely different problem. Not from this thing, but from that chart. Okay. Now, how did they do that one? Well, they drew their best guess of a tangent line in. And it looks like a pretty good guess to me. I'm not sure. I could have gotten one that precise. And then what they did, or what I would have done, let's see if, here it is. Okay, let's blow this up. Now, blowing it up, I'm not going to be able to write on it. But I'm going to show you what I would have done if this had been the data they had given me. Okay? If that's their best guess at the tangent line, now the books look a little bit better than this one, but let's just take them both for what they are. And they picked a point down here, not a bad choice. if they had extended this line further, maybe it would have been better down here. But extend that line until you get as close as you can to an actual intersection. This isn't bad, okay? This gives you exactly at 448, but just short of minus 50, I don't know how many little dots are in there. Let's say minus 51. So that'll be minus 51 at 448. And then pick a point up here. Now they picked one in the middle, which I don't like to do. I would have chosen maybe this one here. That looks right around negative 15 degrees at exactly 1424. So I would have picked 2 points, usually as far apart as possible that you can get as good a guess as possible. Now this may not have been too bad. I don't know how many minutes are here. 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're not very evenly spaced there. I was trying to do the darker ones. Sometimes they have 2 dark ones in a row. Whatever, but if you could figure out how many, not pixels, but close to pixels those were there, and if it came anywhere close to, oh boy, that's quite a difference there. So I think I would have gone to 924 because that's exact, and this would have been right around 15, negative 15. And then come over here and done 448 because that's exact, and make that negative 51. That would have given a really good guess of the slope of that line. So again, let's pick out, what did I say? Okay, I'm going to have to, if I write on this, it's going to reduce. Right here, I'm going to say, I'm guessing that point is 1424, comma, and I was guessing negative 15. And the one down here was 448, comma, minus 51. Now notice we're not taking data points. We're drawing our best guess of the tangent line and picking points on the tangent line so we can estimate its slope. Okay? Same way we did before. Let's do our y2, which this would be your y2 here. Negative 15 minus negative 51 divided by 1424 minus 448.
Real quick, are we taking the slope of the secant line or the tangent line?
They drew their best guess of the tangent line through this point.
Okay. Is that why they didn't extend it down to the other data on the graph?
You mean on down here?
Yes.
I don't know why they did.
Okay.
I would have gone down here just so I could, because it looks like it's heading right there.
That's
that
what
would have
I'm
been a better point.
Right.
But maybe it wouldn't have been. I don't know. And I think this is the best because you see, I can estimate more easily here. There's only 10 points in between here. Here we've got, 4 hours and 42 minutes. Such a weird number there to do that. So I'm going to pick out things on these lines.
Gotcha.
So this one's going to go beyond that. So on here and here. The slope of that line is the same wherever you choose. So just pick 2 points that you got pretty good estimates for.
I see what you're, okay. Gotcha.
Yeah. Okay. So,
Positive, what is that, 26?
yeah, but it looks like, no, more than 20. 36. 36 over, now again, the subtraction of military time here, somewhatly, except you don't have to go to military time, it's already fine. So that'll be a 6 there, that goes to 1, borrow 1 hour here, and that becomes 7, okay, minutes. Here we have Samaria. So 3/4 of the class is here. Hopefully the last one will come in sometime. You beat the first class. They only had 2 show up. You got 3 so far. Good deal. Okay, so that would be a 3 here, and that would be 9. Okay, 9 hours and 36 minutes, and 36 over 60 would be 6 over 10. So that's 9.6 hours. So divide that by 9.6, and what do you get? Second? 3.75, and that would be degrees Celsius per hour. Okay. Now again, pretty hefty numbers. I don't know if this in any way resembles what they were doing before. Let's just see, 542 would be somewhere here-ish, and that would be a minus 74. Now this must be a different day. Okay, I don't know. This was July 6th. The other was just sometime in July, but it doesn't seem like it's matching too well. Okay, but anyway, you get the general idea. Let's see how they did. They rounded it to 33.7 degrees Celsius per hour. Oh yeah, they used the point here, and how in the world they estimated these numbers here, I do not know. They have a lot better judge of things than I do. They probably have it because they had it on a graph, maybe on a computer screen, and they picked a point and it totally goes with the digits. I don't know, but you see we got awfully close to the same thing. Okay, good deal. Any questions on that? Let's move to example 2. All right. Now, what they're saying here is let A equal pi r squared. What we're doing is area of a circle, obviously. Okay. Be the area of a circle of radius r. Yeah, that's what it is. I'll say, what did it say? Let it be, it is. Okay. Number A. Calculate or compute dA dr at r equal 2 and again at r equal 5. How would you do that?
So you would take the derivative.
Take the derivative first. dA dr would be 2 pi r. Okay?
And then you would plug in.
So dA dr at r equal 2 would be,
2 pi, and then parentheses 2.
which would be
Is that
4
4 pi?
pi,
No.
and dA dr at r equal 5 would be
10 pi.
what?
10 pi.
10 pi. Okay. 10 pi. Okay, because it's 5 times 2 pi is 10 pi. Okay? Now, B parts here says, why is dA dr larger at r equal 5? Why is this? I mean, not just a little larger, way larger. Okay, it's certainly a larger starting thing, but think of what we're talking about here. Let's say this is when r is equal to 2.
Right. The radius.
That's your area of the circle. And then as you're expanding that, and you're assuming you're expanding at a uniform rate of your radius, your area is getting larger faster. Why?
Because
As
r
the
squared.
Yes, as r is increasing at one rate, the area is increasing at the square of that. So here you've gone up by 2.5 times. If you take 2.5 and square it, you get 12.5, right? I believe that's right. So then the area would have increased 12.5 times. This was increased it at 2.5 times. That would be 12.5. And I think, so the area is increasing faster, and then you do 12.5 divided by 2.5, and you get a 5:2 ratio, which is what you're doing here. So sure enough, that is, well, yeah. So anyway, that's why the rate is increasing, because the radius is increasing, let's say linearly, but the area is increasing quadratically. In other words, by the square. Okay. And I think this next figure is trying to show that. Okay. Okay. Now, yeah. Okay, what this is showing is area as a function of radius. At a small radius, you have a small area. At a larger radius, your area is much bigger. Not just 2.5 times bigger, but 12.5 times bigger. Much bigger. Okay? So the rate at which this is increasing is here. Here's the rate at which is increasing there. So you see that is much, much faster. And here's the pictorial. This is the delta R when you're start at 2 and change a little bit in radius. This is the amount of area increase. If you increase that same delta R here, look how much more area is increased. Because if you add all this pink together, if you had a way of measuring that and then measure this is many times greater than that, as we saw, about 12.5 times greater. So the rate at which the area is increasing is faster because there's much more area at a larger radius than that. And if the radius is changing at the same rate, the area is changing much, much faster. Okay? Does that kind of make sense? Now, sometimes, especially for small values of h, which usually we let h be very small, the h is approaching 0, remember? The difference quotient is close to the derivative itself. When that h is small, you're already really close there. Because remember that f prime of x at x0 is the limit as h approaches 0 of f of x0 plus h minus f of x0. This is our definition divided by h. Okay? That's what the limit is. That's what your derivative is. So, as long as the h is small enough, it's not going to be far off from this, f of x0 plus h minus f of x0 divided by h. It's going to be very close to that if h is sufficiently small. And that's exactly what we've got here. I just wrote it again because writing on this it reduces that. So this is approximately equal when h is very, very small. Okay? We saw that. Remember when we did our tables before and you got smaller and smaller h's? What you're getting toward is the limit. It would sometimes be with 2 digits and 3 digits and 7 digits. So it's getting much and much closer to what that limit actually was. Okay? So here's example 3. In other words, f prime of x0 is approximately equal to the change of f caused by a 1 unit change of x when x is approximately x0. Okay? Now, I know what they're saying, okay? And here's what basically it comes down to. If f isn't changing much per unit, then to substitute h equal 1 in there is not going to be a bad choice, okay? So here's an application of that, okay? If you let h equal 1, then this will be f of x plus 1, this thing, okay? If 1 is sufficiently small. Now, if your function is changing hugely in a very small difference, this isn't going to make any sense. But if your function is changing very slowly, or let's say your function like we were looking at before, the unit change there was between the tick marks on that Mars data was 5 hours or something like that. So 1 hour is going to be a huge amount of that. So that's going to be a pretty small fraction of it. So then put a h of 1 and a divisor of 1. So that just is over 1. So this is not far from here. As long as it's not changing too rapidly, either your x's are far, far apart, so 1 isn't very far from it, or it's a very slowly changing function. This is not a bad guess, okay? Now, I can think of many examples in nature that would be a terrible guess, but there are others that it wouldn't be bad. For instance, the rate of change at which the Earth is moving at this time of year, we are moving ever slightly closer to the sun because we're going from near spring, late winter to early spring, right? So we're getting a little bit closer to, no, I'm sorry, wrong. Where we are on the globe is getting a little closer. Actually, I said it wrong. I don't know if you knew this. In early January, we're the closest the Earth is to the sun. In July, we're actually the furthest. But the thing is, we're tilted away. And that's why we have winter in the northern hemisphere. The distance is not that big a difference. But the tilt of the Earth and how much direct radiation we get from the sun, that's what makes the difference in summer and winter, not how far we are. We're not far. Our orbit is not quite circular. It's slightly elliptical, but it is exactly opposite of what you would think. So actually right now we're getting a little further from the sun. So let's go back to that example. Going a little bit further from the sun. But it's not very much between here and here. So in 1 day's time it's almost nothing. So this would be a great approximation of what that difference would be. Okay. Sorry, I botched that explanation pretty badly. So let's look at example 3, which I'm not sure is as good an example as that one, but at least it's in the book. I don't think they have a slide for it. Pretty sure they don't know. They do not. Stopping distances. For speeds between 30 and 75 miles an hour. So S is going from 30 to 75 miles an hour. Okay? Now, guess what? 1 mile per hour is not very big in that range, is it? Okay? So therefore, to do a delta speed of 1, that's going to be pretty close to 0 for that range. It's not a big fraction of that difference. Okay? For speeds S between 30 and 75 miles per hour, the stopping distance of an automobile after the brakes are applied is F of S is equal to 1.1, it really should be approximately equal to because I don't have that kind of greater precision, plus 0.05 S squared. Okay. So, at S equal 60 miles per hour. Okay? At S equals 60 miles per hour, it's not going to be a lot of big different stopping distances as it was at 60 miles, 60 and 61, right? Not going to be a lot of difference. So we'll take S equal 1 and use this approximation to come up with approximately what your F prime of S is. And this will be approximate. That whole equation is approximate. That would be 1.1 times, I'm sorry, I put the parentheses in the wrong place. Okay. That would be 61 plus 0.05 times 61 squared minus 1.1 times 60 plus 0.05 times 60 squared. Okay, doesn't matter where you put the parentheses on that. So if someone's got a calculator, now remember.
67.1 is 1.1 times 61.
Say this again.
67.1.
67.1 plus 61 squared times 0.05. 0.05.
186.05.
Minus, now let's try to do this one in parentheses. Open parentheses, 1.1 times 6, I can do that one. That'd be 66, right?
Oh, yeah, sorry, yeah.
Yeah. 66 plus 0.05 times, I can do that one, 3,600. Okay. Let's add those together. We'll multiply this first.
180.
Huh?
180.
This over here? Okay, plus 66 is 246.
Yep.
Okay, so that'd be 246. And what was this one? You added that together. 253.
Yep.
253.15. Okay, take the difference of those two and you get approximately 7.15. But I think, since we're approximating anyway, about 7. About 7.
They got 7.15 in the book.
Oh, they did. Okay. I don't think they have the legitimacy to go that many digits. Well, they did 7.1. Yeah. Okay. So, yeah, they did 253.15 minus 2. Yeah. I'm sorry. I did it the long way. Sorry. They wanted me to do it I did the B part. It says, estimate the change in stopping distance if the speed is increased by 1 mile per hour. I thought that's what we just did. Oh, no, okay. If we did, let's do the F prime of S, the actual, would be 1.1 plus,
Are we taking the derivative?
yeah, taking the derivative.
So 2.05?
Say again?
Would you? Okay, 0.05 s squared. Is that what you're?
Yeah, taking the derivative of that.
Down. Would you? So you would bring the 2 down, right?
Right?
So, yeah.
0.1 S.
Yes, yeah.
Right, okay? Now, and if you're approximating that, 1.1 plus 0.1 times 60, that would be 1.1 plus 6 is 7.1. And this gave us 7.15. And you know what?
That's pretty.
This was easier to do than that.
Yeah.
Hey, this supposed to be your approximation, well, guess what? It was easier to take the derivative and plug it in than it was to approximate it.
Right.
And of course, you get a more precise number anyway. But so I don't see the point. This was not a good example, but I mean, it was a great example. But it seems like to me they've done it backwards. Their A says estimate the change in stopping distance if the speed is increased by 1 mile per hour. That would have been the first thing we did. Oh, they may have done it right. No. They took derivative first. And then it said compare your estimate with the actual increase in stopping distance. It seems like they did them backwards here. The actual change in stopping distance was F at
Oh, I see 7.1.
yeah. Well, I guess they said in the estimate is taking the derivative, right? Just taking the derivative at that point. Yeah, that's what we did. And then they said the actual change is the other. I'm sorry, I did them backwards, but yeah, that's what they did. All right, here's a place they use this a lot more frequently. They call it the marginal cost in economics. Okay? When you see marginal, especially in economics, okay, hit the wrong button again. I don't know why I'm doing that so badly today. Okay. When you see marginal, that means change. Okay? I don't know why they use that, but in economics they always do. And in many things like this. Marginal cost in economics. Let C of X denote the dollar cost, including labor and parts, of producing X units of a particular product. The number X of units manufactured is called the production level, and to study the relative relation between cost and production, economists define a marginal cost at a production level X0 as the cost of producing one additional unit. So marginal means a little increase, a little bit of increase. Now, although C of X is meaningful only when X is a whole number, economists often treat C of X as a differentiable function, X, so that it applies the technique of calculus can be applied. What they're saying here, the cost of an air, well, we haven't gotten to that yet, but we're going, okay, let's go and read the problem. The cost of an air flight. Company data suggests that the total dollar cost of a certain flight is approximately C of X, where, oh, they don't have it on here, do they? If I go to write it, it's going to shrink it, so might as well shrink it. Okay. The cost of flying X number of passengers is equal to, and this, to me, this is approximately even to begin with, 0.0005 times X cubed minus 0.38 times X squared plus 120X. Where X is the number of passengers. Okay. Okay. Now, what they're kind of saying here, if this is your number of passengers, okay, so the distance between here and here is 50, between here and here is 50, between here and here is 50, here and here is 50, here and here is 50, okay? Now, in reality, this is not a continuous function because you see your horizontal axis are only integral numbers, you know, one person at a time. They don't fly fractions of people, okay? Please, that's gory, okay? You fly whole people, okay? But on this scale, one person is a very small entity here. You got to get 50 in between here and here, or here and here. So actually, they're so close together that it almost looks like a continuous function. So therefore, we'll treat it like that, okay? Now, what they're saying here is, and you kind of have to go back to your definition, and this is a little on the wacko side. And here's what makes it wacko. This isn't very realistic at all, because here you have 5,000, 10,000, 15,000. Looks like this is zero down here, doesn't it? So what if you were flying the flight with 0 passengers on it? You think it would cost you $0? No. No. It would cost all the cost. So this is just not a very realistic graph anyway. Say again? They went where? Down here to 50s. Okay, so this is 0, 50, 100, 150. This is 0, 5,000, 10,000, 15,000. So their graph doesn't make a lot of sense here with this. Now, because this should be offset, not at 0. Okay. But if you plug in a 0 here, you get 0 there. So the graph is not very realistic. Probably in this range it's realistic, but down here it's not. That function is not realistic because with no passengers, unless you just don't fly, but then one passenger is going to have enormous costs. So it's not good down here near 0. Maybe up here it makes sense, but not down there. Okay? Okay. Because you have to have some fixed cost in here, and they don't have it. So that's what makes this example a little wacko. But up in this range, it may make perfect sense. Okay? So, what's the question? Company data suggests this. What is this? Number A, estimate the marginal cost of an additional passenger if the flight already has 150 passengers. So we're at this point in the slope, what would be the approximate cost of one more passenger? Okay? Well, the easy way to do this would say that's about your derivative. So let's say what C prime of X would be then. Okay. And then if we plug in here 150, C prime of 150, this would be approximately 150 squared is what? 22500? I don't know. Get your calculator and do it. Do you have one? 0.0015 times 150 squared minus 0.76 times 150 plus 120. 79. Is that what you said? I couldn't hear. No, that's not what they get. Okay. All right. Zero 0.0015 times 150 squared minus 0.76 times 150 plus 120. What did you get that to be? Is that how you did it? Yeah, that sounds reasonable. What? 39.75? Okay, yeah, that's what they got to. About $39.75, $39.75. Okay? When's the last time you saw an airfare like that? Okay, this is an old book, okay, or old data or something, okay. Now, what would you have if you had done C prime at 200? What's the marginal cost there? Adding one more. That would be 0.0015 times, and 200 squared I can do 40000 minus 0.76 times 200 plus 120. Okay, it might be painful, but I think I can do this. That would be move this decimal 4 places here, and this decimal 4 places there. 4 times 15 would be 60 minus 2 places there, 2 places there. That would be 152 plus 120. So that would be 180 minus that would be 28. Is that right? No. Yeah, 28. Marginal cost of adding one more passenger to a load of 150 would be almost $40. And if you had 200 passengers and added one more, that marginal cost would be only about $28. So that's considerably less. That's because the slopes are different on those parts of the curves. Okay. Now, what they're asking for here, using the curve, that makes sense. Their curve in their equation doesn't make sense, especially near zero. Yeah, because the cost of air flight has to have some fixed cost to it. So their problem, okay. So that's estimating the marginal cost. Already has 150. Compare your estimate with the actual cost of adding another passenger. Well, to do that, we would plug in here 151. So you would do the original thing, not the derivative. C of 151 would be 0.0005 times 151 squared minus 0.38. I'm sorry, that was cubed here. First one. God. Okay. Cube minus 0.38 times 151 squared plus 120 times 151. Okay. Now, if you do that, okay, and that's awfully ugly, but if you do 0.0005 times 151 cubed minus 0.038 times 151 squared minus or plus 120 times 151, messy numbers but doable. Okay, then subtract from that the cost of 150 passengers, which would be 0.0005 times 150 cubed minus 0.38 times 150 squared plus 120 times 150, and do that one and find the cost of one more passenger. Probably going to be just a tad less than that. much less. 39 something, 38 something, I don't know. They get 39.60 rather than 39.75. You know, for 15 cents, this is a lot easier. Okay, that's all your difference is. This is so much easier than doing that. Okay. Second. They got 39.60. They did that cost 0.0005 times 151 cubed minus 0.038 times 151 squared plus 120 times 151. Write that down, put it in memory, whatever. Subtract from that 0.0005 times 150 cubed minus 0.38 times 150 squared plus 120 times 150, and subtract that answer from the one you got before, and they said it was 39.60. I don't have a calculator, and I'm not about to try to do that in my head. I can't. I would have to write it down, and I don't want to do that. They said it's about 39.60. But then, when they go up to 200 passengers, not 150, they did it again. Is it more expensive to add a passenger when x equals 50 or, when x is equal to 150 or x equal 200? It's more expensive to add at 150. Okay, 39.75 is a lot greater than 28. Huge amount difference there. All right. Make sense? That's what they call marginal cost. Okay. Now we're moving to another application, and this is one of linear displacement, basically. Okay? Linear motion. And here it says, in his famous textbook, Lectures on Physics, Nobel laureate Richard Feynman, I didn't realize he died in 88. I thought he lived longer than that, but anyway, only lived 70 years. Uses a dialogue to make a point about instantaneous velocity. Policeman, my friend, you were going 75 miles an hour. The driver says, that's impossible, sir. I was traveling for only 7 minutes. Yeah, that's not what the cop was talking about. Nor would you say, oh, but my average speed was only 60, okay, or 50, because I had several stops a long time ago. So that was just, no, that won't work either.
You shouldn't have seen me going down the road. Just so you know.
Yeah. Recall that linear motion is motion along a straight line. This includes horizontal motion along a straight highway, vertical motion of a falling object. If S of t denotes the position or distance from the origin at time t equals 0, velocity is then the first derivative of that time. So if S is your displacement, v would be ds dt. Now, one of you's had some physics, the other two haven't yet? Okay, not probably since high school or something, right? So, if you don't know this yet, I guess I'll go back and write it. Yuck. Okay, write it down here. If S is, I'm pretty sure they said position or distance, S of t, and they say this is position, I can't spell, or this, what's the other thing they have? Position or distance. I like to use the term displacement. Okay, from some point, and they call that, they don't say from the origin, they say from the origin at t equals t, or at time t. Okay, then velocity as a displacement of time is ds dt. okay? The velocity is always the time rate of change of displacement. I don't really like to call distance because distance is always positive and displacement isn't, okay? So that's why I like to do this. The sign of V of t indicates the direction of motion. For instance, when I backed out of my driveway, I was going a negative velocity. I was going a certain speed down the drive, but that doesn't matter. My velocity was negative. My speed was still the absolute value of that. Okay? So the sign of SIG and sign of V of t indicates the direction of motion. For example, if F of t is the height above the ground, then V of t is greater than 0, indicates the object is rising, okay, because it's going upward. Speed is defined as the absolute value of your velocity. So speed of time, and they don't give, that's why I really don't like S, because S sounds like speed to me, but it's really position. But when they say speed, they either spell it out or I put SPD. That's equal to magnitude, absolute value of velocity. Okay. Now, this figure here shows position of a car as a function of time. Now, I hit it again. Keep hitting the wrong buttons. Okay. Now this car is going in a straight line. Okay? It's not turning. This doesn't mean it hits a curve there. It's not what it means. That means the car is this many kilometers away from the origin in this many times. At time t equals 0, it's sitting at the origin. That's where it starts. It starts off sort of slowly because it's not changing its position very fast with time, but then it speeds up, but then starts slowing down, and here between 2 and 3 hours, it stopped because it was at, what, let's say 160 kilometers from home there, and you're still 160 an hour later. I think they stopped to eat lunch, okay? Should have had a late breakfast, should have kept them, I don't know. And then it took off and got further from home, but at some point stopped and turned around and started coming back toward home. It missed a turn. No, I'm sorry. Yeah. Okay. And came back and then stopped for a while, looked at the map, and then proceeded on. I don't know what this means, but that's what's happening. This doesn't mean the car is turning. This is linear motion, straight line motion. They drew it upward. I don't usually think of it as upward, but you could be going due north. I don't care. But anyway, it's going at 1 hour and 75 miles from home. Does that mean it was averaging, it did average 75 kilometers per hour, I said miles, kilometers per hour, but it wasn't always going that. Here it's going less than that, here it's going, I don't know, it could be a little faster than that maybe. In less than 2 hours, it was already 150 kilometers, so obviously the average is greater here than it was here because this average was 75 in the first hour, and it's greater than that in the second hour, okay? But it's already begun to slow. And then it averaged 0 for this next hour. It was at 100, say 60 here, it's still at 160 an hour later. So its average has really decreased there. And then it took off and looks like it maybe even went faster than it is back here, but then stopped, came back, backtracked for a while, and then turned around and went back, stopped again, and then turned around. But still it's straight line motion, so it did this, and then this, and then that, you know. Rate at which it did, that's the slope of that curve. Okay. Kind of a weird trip, but so you tell me. Now, here's another term. They're using speeding up or slowing down. What you're talking about there is actually whether you're accelerating or not. Here, you're starting at 0 and you're increasing speed the whole time, right? So you're increasing speed, in other words, your speed is increasing, but But somewhere up here, even though it's still a positive speed, the speed is decreasing because the slope now is down. Okay? So the speed is actually decreasing until up here at 0. So it's increasing speed, speeding up here. Somewhere along here, it looks like it's going fairly constant speed, because that looks like it's almost the derivative would be a straight line. But somewhere up here, it's slowing down now, stopped, and here the speed was 0 in here, and then really increasing speed here, stopped again briefly, and then started backing up, backtracking, coming back here, stopped again, and then started going forward again. So that's the concept of speeding up or slowing down. Standing still, that means that graph is horizontal between hours 2 and 3. Returning to the same spot, it rises and falls and coming back to the same spot. Now there's no curve in there. It's the same spot. Went up, backed up, came back. We came back to the same spot there and sat there at 4 o'clock, 4 hours later, and then started going shortly after that, speeding up. So the average velocity would be from any 2 points. You would take the displacement divided by time. Like I said here, this is 75 kilometers per hour. This was, let's say, just figure the difference in kilometer in ds, delta S over delta T. That's average rate. So a truck enters, example 5, this is not example 5. A truck enters the off-ramp of a highway at t equals 0. Its position after t seconds is this one. Is this it? S of t, no, not quite. It is, but they don't give it to you. S of t is equal to 25t minus 0.3 t cubed. That would be in meters. And this is good for 0 less than or equal to t less than or equal to 5. And that's usually in seconds. Yeah, t seconds. Okay. Now here's what you got going here. Initially, the truck was going along, batting along at a good speed because it entered the off-ramp. Okay? Went out of the expressway onto the off-ramp and is going to need to stop by the bottom of the hill, or at least slow down significantly. Okay? It may not be at the bottom of the hill, it could be an off-ramp going uphill. Whatever, it's an off-ramp somewhere, and it's starting at a fairly high rate of speed and slowing down significantly as it goes. Okay? So this is its displacement. Okay? How fast is the truck going at the moment it enters the off-ramp? Can you tell that? How?
Really just looking at the graph.
Okay, yeah, but ignore the track graph for now. This is all you know so far.
Would you take the derivative?
Derivative, S prime of t is going to be v of t, which is how fast it's going. And what would that be? 25.
Minus 0.3 t. Excuse me. Let me back up. 0.6.
One more time. This is a 3. 0.9, okay. T squared, okay. And that would be in meters per second, by the way, because this is ds dt. And that shows meters per second, okay. All right, and at what time it says, I've lost my place, oh, here it is. Truck enters the off-ramp at time t equals 0, okay. So, when it first entered the offer app, what time was that?
0.
0. So plug in a 0 there,
So it's just
and V of 0 would be 25. And is that meters or yeah, that's meters per second. Okay, good deal. All right, that answers your first question. B. This was A. Okay. Since V of t is equal to 25 minus 0.9 t squared, now they tell us, is decreasing from figure 7. How can you tell that without a figure 7? How can you tell this is decreasing?
would you continue to plug in
As
values?
you increase time,
Right.
this is 25, subtracting a positive number from it,
Right.
so this is obviously decreasing over time. Yes, so you didn't have to have the figure, but the figure makes sense physically, and it makes sense according to the calculation. Okay? So, is the truck speeding up or slowing down? Slowing down. Later, they're going to give us a better way to do this than what we're doing now. Okay? So, here would be another question I'd have for you. If this is good from t equals 0 to t equals 5, does that truck stop in those 5 seconds?
No.
Yeah, because all it would do would slow to 25 times 0.9. Yeah, that would be 24 point something or 20. Yeah.
It'd still be.
Yeah, it's still a little bit short. If that was 1 times 5 squared, yeah, that would come to a complete start, but it's 0.9. So no, it doesn't quite get there. It does slow down. And that's why, sure enough, it doesn't show it. It only shows it come, at some slow speed right before at 5 seconds. All right. I think we've done all the things we can do with that. There's the answer. Okay. The truck is slowing down. Okay. Now, this is often called Galileo's formula. Not bad either. I mean, it's pretty reasonable. He pretty much Galileo discovered that the height s of t, now s is displacement, s of t, and velocity v of t at time t seconds of an object tossed vertically in the air near the Earth's surface is given by these two formulas. Your s of t is s0, which is the height of the ball or the object at the time it leaves your hand, as you toss it. V0 is the velocity of it at the time it left your hand, V0. T is the time at which it, after it left your hand. So when t is equal to 0, what does this give you? S is equal to S0, that's where it was right before it left your hand. Okay? Then as t is increasing, this part would tend to increase, but this tends to decrease. So since this is, by the way, G, what in the world is G?
Gravity.
It's the acceleration due to gravity. Okay? And the acceleration due to gravity in U.S. customary units is 32 feet per second squared. In SI units, the System International, is 9.8 meters per second squared. So sort of get used to that. All right. At a significantly large velocity, this wins early, but this starts picking up in time, and then as time, since it's being squared, this catches and passes this. At the point where it passes that, at that instant, the speed is 0, and then it starts coming down. It starts decreasing the velocity after that. The v of t is the derivative of s with respect to t. This goes away because that's a constant. This will just be v0 minus 1/2 of 1/2 is, 2 times 1/2 is 1 gt to the first power. So at time t equals 0, position, S0, initial velocity, V0. Okay. Galileo's formulas are valid only when air resistance is negligible, which means your initial velocity is pretty slow, okay? About the same speed you can usually throw things, okay? We assume this to be the case in all the examples, okay? And like they gave here, G is approximately 9.8 meters per second squared, or 32 feet per second squared, just like I said. Okay. A simple, goodness gracious, head is clogging up. A simple observation enables us to find an object's maximum height. Okay? Since velocity at a position of an object rises is positive as the object rises, negative as it falls back to Earth, guess where it's going to be? 0. The velocity is always positive. I throw something into the air. I have an initial position, I have an initial velocity upward, but this G is always pulling it toward the center of the Earth. That's why the minus sign is there. To begin with, this overpowers that and it's going upward. But at some point, as T increases, this gets bigger. That is getting bigger too, but this is getting bigger faster. At some point, that overcomes and it pauses it instantaneously, and then it starts falling back when this is overpowering that. But think of this, that's at exactly the same time it goes from V0 is positive upward, and then this is slowing it down until that reaches 0, and at that point it quits going up, pauses momentarily, and starts coming down. And that's your experience, isn't it? Have any of you ever thrown a ball into the air and it just kept going? You've launched it into outer space? I don't think so.
Have quite an arm.
Yeah, quite an arm, yeah, but not that good, okay? All right, rockets have a hard time doing it, okay? So, at some point, it will stop, and then the velocity turns negative. So, the place where velocity is 0, that instant when it's 0, that gives you the time of your maximum displacement. Once you get that time, plug it in here, and you get how high that is. So there's the theoretical procedure of how we're going to approach these problems. Okay. So, example 6 says to find the maximum height. I think we're going to use a figure here. And by the way, what is this figure called? I hit the wrong key. I'm doing that too much today. Okay? What's that figure called?
An upside down parabola.
A parabola. Okay, it's a parabola. And when you set upside down, that means it's emptying downward. That means your quadratic term, the coefficient was negative. But guess what? It was minus 1/2 G before your T squared. And G is always positive, 9.8. Square that and it's positive, but the minus 1/2 of that means it's going downward. So sure enough, this will have a maximum height at some point. Now, if you did include air resistance, this wouldn't be a parabola anymore. Okay? It would be distorted some way. We're going to ignore that, so this will be a parabola. Okay?
We'll let him off the hook this time.
Yeah. Okay. Like you've been fishing or something. Okay. So the maximum height does occur when your first derivative as a function of time, or of displacement as a function of time, that's your velocity, is equal to 0. So it's going up, positive, 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 slowing down, momentarily stops, and then starts coming down again. At that point it stops. That's the maximum height, but it's also where the first derivative is 0. Velocity is 0. So we can find that out from there. So let's see what the problem says. A stone is shot with a slingshot vertically upward with an initial velocity of 50 meters per second from an initial height of 10 meters. That's why they have this elevated here to 10. Okay, that's the initial position. Okay. The A part of the problem here, of course I've got to can that to go back. The A part of the problem says,
find the velocity.
yeah,
T equals 2, and at T equals 7.
okay. Let's go back before we do that, though. I was expecting them to give us, well, what happened? I thought I had something on there. It disappeared, okay. I didn't know I did that, but it did. So, stolen a shot with a slingshot vertically upward with an initial velocity of 50 meters per second. What was in our formula? Galileo's formula was initial velocity. Turn back the page. That equation
V of T equals velocity equals
okay. What is your initial velocity? In that. Okay, let's go back here.
50 meters per second.
In these formulations right here, what represents your initial velocity?
VOT?
VO. VO. Yeah, okay.
Gotcha.
So VO is equal to, I like to write down things as I read them, okay? I can't find where I am. Oh, I turned the page. That's why I can't find where I am. It's throwing a shot with a slingshot vertically upward with an initial velocity of 50 meters per second. So when I see that initial velocity, that V0 is equal to 50 meters per second, okay? From an initial height, what was that represented by? SO. Your SO was 10 meters. Okay. Now, once I have those, I can write down Galileo's formula. S of T is equal to 10
plus
50
minus
50T minus,
1/2.
okay, let's pause a moment here. This is in meters, yeah. So this is 1/2 of 9.8 T squared. What's the second formula? V of T is equal to, which is, say again?
ds over dt.
V, V,
ds.
DS? Oh, okay.
Sorry.
Okay. The derivative of that, yeah, ds dt, which is
V0 minus gt.
minus gt. Okay.
So 50 minus 9.8.
Yeah, okay. Let's go back and do it that way. Because we've already, well, the eraser's not coming up. This is so aggravating. Okay, there it is. Goodness gracious. 50 minus, what do you say?
9.8.
9.8 T. Exactly. Okay. So there are your formulas. Okay? It says find the velocity at T equal 2. Pretty easy to plug, isn't it? V of 2 is equal to,
10 plus 50 t.
where'd you get 10?
Oh, V, I'm sorry.
V, yeah, right, okay.
50 minus 16, 17.6, 19.6.
Okay, which would be 30.4 meters per second. Okay, velocity is in meters per second. Okay, how about at T equals 7? V of 7. Whoa.
So
50 minus
67.
yeah.
Yeah,
So,
it's right. 67.9. Yeah.
that's a 6.
Uh-huh.
Okay. 56, 60, that would be 68.
68, sorry.
Yeah. So this would be negative 18.6 meters per second. Okay. I really, yeah, okay. This is the velocity. So basically, you're sometime past your, you have a negative. Here you still have a positive velocity. Considerably less than 50, but still positive. Over here, you have a negative velocity. Okay? I know we're out of time. And I think we just explained the change of sign. So what we'll do here is start on the B part next time. Homework exercises here include any of the odds 1 through 7, either 9 or 11 or both. Any of the odds 13 through 'Goodness gracious. There's a pencil and a half here, aren't there? Try to do any of the odds 13 through 37, I think. If you can't get all those, hang on and we'll pick up. And maybe when we go over the additional stuff in class, you'll get it. But if not, we'll work some of those in class if you can't get them all. Okay? And we will wrap up then this. I thought we might get through it, but we'll finish 3.4 next time, move on to 3.5, which is a fairly short section too. Then we'll do the trigonometric functions, which is a short section. Then we'll do the chain rule, which is a little longer. Okay, this is a long chapter. And then we'll do implicit differentiation, which is a fair amount there. And let's see, it just keeps on going, doesn't it? Derivative of general exponential and logarithmic functions, we'll do those. And we'll skip the hyperbolics. Okay? I'll go over quickly the slides for them, but I won't hold you related. And I wish we had time for related rates, but I really think by that point we're going to need to go and do the test. But related rate problems they really are a lot of fun. It's just that we don't have a lot of time to do it. All right, so we getting close to halfway through this chapter. This is a long chapter, but hopefully we'll pick up and go a little faster. Good deal.